My name is Joel, and in this video, we'll actually be walking through another vulnerable VM, which is called the Brainpan. Right? You can do a quick search on Google, and you will find a download link for the Brainpan. And once you download, you can import it either on VirtualBox or on VMware. I'm actually using VMware Fusion for this. All right. So the things which I'll be needing for this particular demo is the Brainpan VM, obviously, because it is the victim machine. Then I also have my Windows machine which I'll be needing, right? So I also have a Windows VM, which is also present in the on the VMware Fusion, and I have my attacking machine, which is the Kali machine as usual, right? So let's start with checking if I have um, IP address. So my IP subnet which I'll be using for this exercise is 192.168.16.215, right? Great. So let's start with net discover to find the IP address of my victim machine. Give it a minute. So I think I've got it. Let's start this. So it's either 217 or 218, right? So I believe 218 is my Windows machine. I can quickly see here. So my Windows machine is 218. So which means that my Brainpan machine is actually at this particular IP. So let me put this down in my notes. Great. So I have the IP address. Let's do a quick nmap, right? So if we do a quick nmap, for what? Let's do an nmap for an A and the IP address, right? You will get to know the various ports and the services which are open on that particular vulnerable VM. Give it a second. It's still trying to figure out. Hope my VM is up. Yeah, so this is the VM. It's up, and we should have the results any minute. So while that processing happens, let me also tell you that in this particular exploit, we'll be actually doing a lot of buffer overflow exploit, right? So buffer overflow is kind of like the crux of this particular vulnerable VM. I will paste the links for a couple of very interesting talks on buffer overflow, which I found very interesting and very useful. So you guys can refer to that before venturing into the actual hands-on of this particular exploit, right? So now you have seen this. We see that there are a couple of ports which are open. One is the 999 port and 9999, and the other one is a 10,000, right? Let's take this for now, paste it in our notes. So it's great. There are two ports. Great. What do we do next? So let's look at the port number 10,000, because it seems to be like an HTTP port. So what do? I need to open my browser, right? So it's 192.168.16.217, and the port number being 10,000. So if you go here, you can see that this is basically the HTTP port which is open on the vulnerable VM. Let's see if you can see some view page source. Okay. Unfortunately, it's just like a image, right? There is nothing which we can fuzz over here, right? There is this this web application doesn't seem to have any kind of fuzzing opportunities. So let's focus on the other port which is open, right? So the other port is the 999. So how do we do this? But before that, let's also use the Derby. Let's also use the Derby, which we have been using a lot, to kind of like scan the website in case if we left out some information, right? So what we could do is we could just take the IP address from here. copy, let's paste it here. There we go. So it's scanning. Give it a second. Any useful info? Okay, I see we have got some good information here. It basically found out that there is a particular folder called as the bin folder. So this is good information. So let me paste this over here, store this information. This could be useful, right? So we have a particular folder, right? Can we access that folder? So what do? We just go to the browser, put in the slash and the bin. The proxy, okay, so there is some proxy which is being set up. So I'll have to either turn off the proxy or just turn on burp suit. Let me just turn on burp suit. It's probably from an earlier project where I had set up the proxy. So yeah, instead of turning off the proxy, I'm just turning on burp suit. Right, so let's go to proxy, intercept is off now, and now I'm not using burp suit anymore, so I'm going to refresh this. You can see, yes, so there is an exe file. Looks like there is an exe file at this particular location. Thanks to Derby, we were able to find this. Now, what do? It looks like a exe file. So how about we fuzz this exe file on Windows machine? So that's why we are basically using the Windows machine. So we come to Windows machine here. The first thing is we'll have to download the exe, right? So we'll have to just go down to 192. So this is the place, right? So here you have the exe. So you download it. I've already downloaded it. It's on my desktop over here, which is pretty good, right? So we will be using our Unity debugger a lot here, right? So the Unity debugger is on. Okay. Wait a minute. Let me restore the defaults. Is that possible? Okay. Anyway, so let's try to open. What we are going to do now is you're going to run the brainpan.exe, which we have downloaded, right? Which we downloaded from the Internet Explorer. Right? We are basically going to open that exe file using the Unity debugger. So we are going to basically open it here, right? And we will. Okay, I think we need to rearrange this. It looks really bad. Give me a minute. Let me try to do this. Okay, let me just close all of these. Right. So okay, we also close this. Okay, shut this and open the see over here. Let's see if we have something over here. Yeah, okay, so I think we got the 4 windows. It's a little troublesome. The windows gets distorted. I have to still figure out how do I get the default view. I think, yeah, so this will be good. Great, so this looks good. This is basically like the default view, right? So we have opened our brainpan.exe using this. What do we do next? Let's go and hit the run button, right? So you can see here it's running. So the Unity debugger is basically running the brainpan.exe. Great. So now what do? Go back to Kali and let's do another nmap, but this time we are basically going to do an nmap. It's going to be very similar to the earlier one which I did, right? It's just that I'll be changing the address from 217 to 218 because I'm trying to now look at the services which are open on the Windows machine, right? Great. So that is done. Now, if you observe carefully, the services which are running on the Windows machine are also pretty much the same as the ones which we found earlier, right? When we did the nmap on the Brainspan machine itself, right? So you can see the similar kind of ports. You have 999 running here. So it kind of makes us believe that the Brainspan exe is actually using this port, right, 9999, and the rest of the things almost look same. So let's start fuzzing this service, right, which is running on this particular port. Now to fuzz this particular service, what we have to do is there are certain template, right, for fuzzers which I downloaded from the internet. I will provide you this links as well. There are a bunch of fuzzers which I downloaded. It's here, right? So these are the various fuzzer, the Python files which I'll be using. I'll provide you guys the links to this, so don't worry, I'll be providing in the description, right? So these are the fuzzers which I'll be using, right? So let's open up the fuzzers. Let's go to desktop, let's go to Brain Master, right? Clear the rest of the screen, right? So let me show you some of the things which we'll be using, right? So let's start with the first one, which we'll be using is the, open it and get it, Brain Fuzzer, right? So this is going to be the first fuzzer, right? So what this particular fuzzer does is it takes the character A, right, and tries to provide this as an input. So what we are trying to do is we have this exe file which is running over here on the Windows machine, and we are basically trying to provide input to this exe file, and we are trying to do a buffer overflow, right? So we'll be increasing the length of this by 100. So we have a counter of 100, so we're going to increment it until it reaches 4000, and we are trying to figure out at which point it crashes, right? So that's the whole plan. And this particular program takes two inputs. One is the IP address, and the other one is the port number on which we are trying to fuzz, right? So this is pretty straightforward. Like I said, I'll provide the links to these Python files or codes in the description. Perfect. Let's start with this. So we're gonna fuzz, right? So we're gonna do Python brain fuzzer.py. The IP address is 192.168.16.218, which is the Windows machine, and the port is going to be 9999. Right, so there you go. It the code basically ran, and it says that it kind of crashed at 1000 at 900 bytes, right? So this was the last connection which was successful, whereas the 1000 did not go, right? So what happened was this particular script went on fuzzing the brainspan.exe with 100 bytes of character A, and it incremented, went up to 900. 900 was successful, but 1000 was not, right? So so our capability, or the buffer length, is somewhere between 900 and 1000, right, which is good. So we have that information now. So what do we do next? Stop this, right? So now let's try to find a pattern. So Kali Linux has this amazing tool which can help you create patterns, right, which is very useful for creating a buffer overflow exploit. So let me show you what this pattern creation is. So let's try to locate this. Where is this? Probably somewhere here. Yeah, there you go. So this is the pattern create Ruby file which I was talking about. So we'll take this, we'll paste it here, and what we are going to do is we are going to tell this particular Ruby file to give me a good pattern which I can use for testing my buffer overflow exploit, right? So the size of this buffer is 900, so we realized that. So I'm going to give 900. Yeah, there you go. So we've got this, and what we are going to do this is we are basically going to use this pattern in in the next fuzzer which we are going to use. So earlier we used a fuzzer where we were just inputting the character A, but now we are going to basically use this particular fuzzer. So what we are going to do is, let me open the okay, let me just quickly see what's the name of the file. Okay, it's this one. So I have to open this one, which means let's do get it brainspan1, right? Tap, get the spelling right, brainpan, sorry, my bad. So if I open this, what we are trying to do is, this is the pattern which we are going to replace, right? So this is the place where we are going to put the pattern of our choice. In our case, we are basically going to put the pattern which we just now created, right? So let's push this. Sorry, not this. I think I copied the wrong thing. Let's go and copy this again. This is the pattern which I'm interested, and there you go. So that's the pattern, and it looks good, right? Let's see this. Great. So that looks good. So that's the pattern. Let me probably save this. Turn this off. Okay. So now we have to so every time we fuzz it, we'll have to stop the debugger and run it again, right? So let's stop this, open it again at this one. So it's running. Let's hit the play button and let's come back here. And we are going to run Python. This time we are basically going to run brainpan1, right, .py, with the same IP address and the port number. Okay, there was a mistake in the code. Give me a minute. Let's check this. Make a mistake here, right? I think probably that was the issue. Let's see if this works. Yeah, so it got completed, right? So now what we have done is that we have put this unique length of characters, this unique pattern which we had generated, and you can see the instruction pointer over here, right? So we have got the instruction pointer EIP populated with a particular pattern here. So let's copy this to clipboard, and what we are going to do is let's just paste it here for a minute, right? So what we are going to do is, we are trying to figure out what is the exact offset, right, in this huge pattern. What's the exact offset of the return address, right? So we are going to use another Kali tools, right? So which is called as the pattern offset. It's again another Ruby script. I'm going to use this. Sorry, let's do allocate, right? So this is the Ruby script, and so we'll take this, copy, paste it, and we are going to give him the offset which we got here, right? So this is the offset. Let's come down here and let's paste the offset. Yeah, so the offset is 524, right? So what does this mean is over here, yeah, so when we create the exploit now, we will have to craft a new exploit with 524 characters being, say, of character A, and then the return address and all of that comes into picture. So let me actually show you where that happens. So let me probably open up the next one. Yeah, so this is what it means, right? So initially we started with fuzzing with 900 characters of A, right? So this was the only thing which we did. But what we wanted to do was we wanted to find, I think if you guys know what is a buffer overflow exploit, you know the idea that you need to fill the buffer with a lot of things. You need to fill the buffer to start with. In this case, we'll be filling the buffer with a lot of A's, and then you need to figure out the return address, right? You need to have a mechanism wherein you can dictate the return address, or you can write something into the return address location, right? So that is what we are trying to do. So what we did here was we ended up creating a very unique pattern, and we took that unique pattern and we put it on the buffer, and we tried to figure out what is the instruction pointer having, right? So using the data which is on the instruction pointer, we figured out the offset is 524. So we want 524, but after 524, the next set of data which will be going in will be actually going to the return address location, which in turn will be going back to the instruction pointer, right? And the rest of the data is going to be the character C, right? So that's good. So let's run this and see what happens. So let's again go back and close this, and we'll have to do this again. So every time you have to, right? Let's fuzz this again. There you go. So this time we are basically going to use Brainpan 2.py, right? That got completed, and you can see we are able to completely dictate our instruction pointer. It is now showing 42, which is nothing but the character B which we inserted, didn't we, right? If I have to show you again, this is what we inserted. We inserted 4 B's at that location, and we are able to exactly dictate what our instruction pointer will have. Now, so once that is settled, what we have to do is we have to finally craft our, okay, before that we have to also check for bad characters, right? So we have to check for bad characters because the final aim of this particular demo is to come up with an exploit, come up with the shell code which will reside, that's the whole idea of buffer overflow exploit, isn't it? Right? You come up with the shell code and you make your machine, right, jump to the exploit, jump to the shell code, and then you take control of the whole machine. But what if our shell code has certain characters which are brainpan.exe changes or doesn't render as it is? So we have to make sure that our shell code doesn't have such characters. So what we do here is we have to check for bad characters, and that's where we use the next brainpan.3, right? So let's see what's happening in .3.py. So this is the next fuzzer. So what we are doing is we have a bunch of characters here, right? And we are trying to figure out if all of these will be rendered as it is on the immunity debugger, right? So let me show you this. Let me again go and turn this off, turn this on again. Right, so this is running. So what we do is let's go and run this brainpan3.py. This is basically checking for bad characters. So when you run this, you can see here yeah, so I think that's the max. Let me see if I can increase the size of this. Appearance, font, and yeah, this is a little better, isn't it? Yeah, so if you see here, what we inserted now was that right, so this was a fuzz, right? So this is what we inserted. So we inserted 524 characters of A, then 4 characters of 4 B characters, right? And then it was just the bad characters, right? So now if you see here, we have the A's, we have the B's here, and from here starts the bad characters. We are basically checking, right? And you can see if you start from 1 2 3 4 5 6 7 8 9, you have 0A, 0B, C, D, everything, right? So this is something you have to manually inspect. Go on checking if every of these character has been rendered the way you know input it over here, right? In my case it has, right, except the 00 character, which will not be rendered the same way. So other than that, rest of all the characters seem to be good, right? So let me turn do I have to, let's keep it this way, it's fine, right? So let's close this. So we don't have any major bad characters. Now we need to find the jump ESP address in order to overwrite the EIP, right, or the instruction pointer with it to execute the shellcode, right? So we have to find the jump ESP address. So I'll tell you why we need the jump ESP address once we come up with the final exploit. But for now, let's just assume that we have to find the address for the jump ESP, right? So we have again a NASM Ruby script for helping us figure out what is the assembly code for that. So what we are going to do is run this NASM shell, right? It's on again on Metasploit framework, so you can run the NASM shell. Yeah, so we have the NASM shell. What we do is, let's say what is jump ESP, and it's going to give me the assembly code, which is FFE4, right? So once we have this, what we'll do is we'll come down here and we'll use a module which I've installed with my Immunity debugger called as the Mona module, right? So if you observe here, can I increase the size of this? Probably not. Can I? Maybe not. Okay, so if you observe here, it's going to be I'm going to write exclamation Mona. So Mona is the module. Find. What I'm going to find? I'm going to find trying to find the FFE4, right? I'm doing this so that I can find the address of jump to the stack pointer, jump ESP, right? So it's going to be XFF, and sorry, I think I missed a slash, right? I think I've written it down here. I'm going to just use this. Don't make a mistake. There we go. So it's going to be slash XFF slash XE4, and you're going to give the application name, which is brainpan.exe. So when you run this, you get the address. You get the address which is here of the jump ESP instruction. So let me take this address, copy to clipboard the address. So there you go. So that's the address. That's the address of my you know, jump ESP, right? The stack pointer. Right. So every time it jumps here, right, the stack pointer will get executed, and in our case, since the, so I'll show you this exploit. I think that'll be helpful to understand. So this will be the final exploit which we'll be crafting, right? Okay, let's actually, we haven't yet created the reverse shell, so let's create the reverse shell as well. So for reverse shell, we are basically going to use MSF Venom, right? Let me just pick this here. Yeah, so this is the MSF Venom, which is basically used for creating the reverse shell for Windows. The L port is basically 443, and the L host is basically my Kali machine, which is 192.168.16.215. We are basically going to use Shikata Ganai, and we need to mention the bad characters. In my case, the bad characters were just 00. I mean, that's like the default ones. There weren't any other than that, right? So we're going to run this, and this will give me my shell code, which has to now, all of things what we have done till now will all come together in the final script, and I'll tell you the importance of doing jump ESP and all of that in the final script now, right? So there you go. So this is the final, shell. This is just the shell code which we figured out, right? So what we'll do now is open the final thing, which is brainpan probably 4.py. As you see here, this is the one, right? I've already pasted from the previous exercise, so I'll just keep this. So this is the shell code. So now you can see the final payload here, and everything comes into perspective here. So what we have done is we have retained the 524 characters of A, right? Because this basically fills up the buffer, right? And then what we have the address which we had here, right? We just copied here. It is 311712 F3, but it is little Indian, so we just start putting the things on the right. So you do it as F3 1217 and 31, right? So that's why we have F3 1217 and 31. So this is basically going to be, getting placed on the return address location, right? And the EIP, which is the instruction pointer, will try to execute whatever is there, over here, right? So the this is basically nothing but the stack pointer, and looking at the execution of this particular program, or the brainpan.exe, what happens is the stack pointer basically would be pointing to where this set of characters, right over here. The stack pointer will be actually pointing here. So that's why we have this return address, or the EIP basically pointing, or it's nothing but a jump ESP. We have done a jump ESP over here because of that, because we know that the stack pointer will be pointing to the characters which start from here, right? So what is the rest of the payload? So we have like no ops being put here. I think you guys know what is no ops is. So we're basically doing 900 minus 524 minus the 4 because of this address. So the rest of them are no ops, and after the no ops we are basically putting our buffer, right? So when this executes, we basically end up the machine will try to, or the stack pointer will be pointing to the no ops will get executed, and the buffer will help us gain control of the machine. So let's see if this works. So now we'll before doing this, let's turn off the immunity debugger, and this time run the brainpan exe directly, right? So we are running that, and let's go to the sorry, we had it here. So it's going to be brainpan4.py. Oh, my bad. So I think I forgot to have my I did not create a listener, so let's create a new listener here, right? Because it's sending it back to my Kali machine. So it's going to be nc nlvp 443, right? So that's a netcat. We have the netcat here. Now let's run this. Before running this again, we'll have to run the brainpan exe, right? There you go. So let's run this, and you can see on the left side we have got the shell of Windows, right? Who am I? There you go. I have the user, right? The Windows user. So this was successful, right? So we just learned if this particular exe was on a Windows machine, we could have got access in this way. Now we have to just repeat the same thing so that we get access of the Brainpan VM, which is actually a Linux VM, right? So it appears like a Linux VM, this one. So we have to get access of this one, right? What we did was we just got the access of the Windows machine which was sitting here, and that's probably not our final objective, right? So we have to do some of this exercise again. Let's go back to that. So what we'll do now is, so we earlier run the MSF Venom to generate the reverse shell code for Windows, but we are now going to run the same thing to generate the reverse shell for the Linux machine, because brainpan.vm is a Linux machine, right? There you go. So we're going to run this, and on the other side, instead of netcat, we are basically going to use something else, right? So instead of netcat, probably let's use the MSF multi-handler, right? So let's start with MSF console. So there you go. We have the new shell code here, right, for the VM, for the Linux VM, right? This would basically go inside the final script, which is brainpan5.py, right? So inside this 5.py, so this is the place where the shell code goes. The rest of the things, everything remains same. Only the difference is that we are basically using a different reverse shell, because we are trying to now get the shell access of a Linux machine and not a Windows machine, right? So we have the script ready. We just, instead of netcat, we have decided to use multi-handler. So let's use the multi-handler. I think let's use multi/handler, right? Let's set the lhost to the Kali machine. Let's also set the L port to 443 and payload. Okay, so the payload is basically the reverse shell, and let's run this, right? So it's listening now, and what do? We just go and run brainpan5 dot py, and instead of the IP address of 218, we will have to use the IP address of the machine, which is 217, which is the Brainpan machine, right? So let's run this, 217. Great. So we have the shell here. So we got the shell. Let's say who am I? So I'm a user called Puck, right? But I'm not sure if I can log into root. Can't cd to root, right? So it means that I've got the shell, or I can actually get the other one. So let's actually go ahead and see if we can get the TTY shell before this. Let's try to get the TTY shell here, right? So we are in the TTY shell. Now if you do the ID over here, it basically says I'm not the root. Let's see if root is allowed. No, the root is not allowed. Anyway, so we have to do some privilege escalation now, right? So let's try to find which are the files which have like root privileges, right? Now if you look at this, there are like a lot of files here, but when I did the earlier session, when I did it on the first time, I figured that one of the file here looked very suspicious. One of them, the one was this one, user local bin validate, right? So if I take this file and try to open this, right, it basically asks for some kind of the input, right? So what do you think? Can we do another buffer overflow exploit on this particular file to get to the root access of the Brainpan system? I think that's exactly what we have to do, right? So to do that, let's first probably transport this you know this particular file onto my Kali machine. So let's go down to Kali here. On Kali, let's create a file, right, on the netcat. Do we have any other? Okay, that's good. Right, so let's go to Kali machine and create a netcat session, and whatever is getting, we'll create a file called validate, and we will go to my brain span and connect to this machine, connect to the Kali machine, which is here, paste. Right, this is the IP address of Kali. The port is 4445. Let's use the greater than symbol. Let's use this and paste this. There we go. So what has happened here? I think we should have got a file. Let's see if we have a file called validate. Yeah, we have a file called validate. Now this is the file which we have to fuzz and try to figure out if we can do some kind of, right? So what we'll do now is, right, so let's first change the file properties, or let's make it executable. So we have done that, and let's try to run this with like probably 100 characters of A, right? We're basically fuzzing it, so we'll start with providing 100 characters of A as input. So it looks like it passed and there was no error, right? So let's try the same thing but with 200 characters this time. There is a segmentation fault. Maybe there was a buffer overflow happening, right? So let's do the same process which we did earlier, but this time let's create a pattern with just 200 characters, right? We did the same exercise for Windows as well. Let's go and create it for 200 characters. While that happens, let me create a new window. because what we'll do now is we were using a immediate debugger in Windows, but in case of my Kali machine, right? So why we are doing this is we basically downloaded the validate file onto my Kali machine, and we'll prepare our exploit here and finally go and put this exploit on our Brainpan machine, right? So that's the whole idea. Great. So we don't have a debugger here like immediate debugger, so we are going to use the default one, the GDB one, right? So what we'll do is GDB validate. There you go. And this is the pattern, right? So this is the pattern which we got, the 200 character pattern, right? So we will use this pattern and run it, on the debugger, right? So how will we do this? We're going to paste this here. Give me a minute. Let me reduce the size of this a bit. Yeah, let's paste this here. Let's run this. So there you go, it ran. So when it ran, this was the character, right, which we got, which is good. So now what we have to do is, remember we did this earlier, we are going to run the offset Ruby file to figure out the offset of this particular pattern, right? So let's paste this. Let's give the parameter -q, and let's take this value, copy, paste it here, and there you go. It should give us the offset. Process is almost the same as we did with the Windows machine, right? There you go. The offset is 116. So our new exploit is going to be, so let's quit this again and start it again. So right. So our new exploit is going to be something like this, right? Right. So there you go. So we have like 116 characters of A because the offset is 116, and 4 characters of B, and the rest of them are going to be C. And as you see here, this is the instruction pointer, and this is B, right? Exactly the 4 characters which we put has exactly gone into the instruction pointer, which is pretty good. So we now know that we can dictate where the instruction pointer is going to, what we are going to fill inside the instruction pointer, which is pretty good. Nice. So now next, what do? We will also see the address of the stack pointer. So this is the stack pointer, and it says the stack pointer is actually pointing to the 80 times the C, which is actually part of the exploit which we just now created. But here we are not going to use the stack pointer like we did in the earlier case in Windows machine. We are basically going to use the EAX register, right? So for that, let's also look at the EAX, right? What is happening at EAX? So EAX will be pointing to the start, right? It's actually here. As you can see, this A is repeating 116 times, and you have the B and then the C. So here we're going to use the EAX to point to the exploit, right? Basically the shellcode, right? So it's all going to come into place once we come up with the final exploit. So hold on there. So what we're going to do now is we are going to go down and grep, right? So let's see this. So let's open another, or maybe here. Yeah, this should be good. So what we're going to do is we are going to grep for, so we have the validate file, don't we? So we are going to basically grep. I think this can be quit, or let's see. Okay. So we're going to grep for jump. We're going to grep for jump AX or call AX, right? So let's do this. So let's paste. Sorry, we did not get anything for jump AX. Let's see if we can do something for call AX, EAX, right? We are not using ESP here, we're using EAX instead. There you go. So we have got the instruction, and the address is here. You're going to use this address probably. Let's use this address. Yeah. So we're going to use this address. Let's paste this somewhere. That's the address of EAX which we'll be using, right? Perfect. So what do we do now? We have to figure out the bad characters. Do we have any bad characters? For bad characters, what we do is, let's actually quit this and start again. Right, so for the bad characters, we are basically going to do the same thing like we did earlier. we will run exploit with all the characters. Let's take this, paste it here. So it's going to be this, right? We are basically running all the characters, all the possible characters. We're going to run this, and what we'll do is we'll look at the EX. Let's look at the 100 bytes of the EX. So we do here, you can see that you have your A's here and you have your B over here, and from here starts your characters, right? So I have manually checked all of this and I have figured out that so you can see 1 2 3 4 is good, 5 6 7 8 are also good, whereas 8, right? So after 8 you don't have 9, right? And you don't even have A, right? So you directly starts with B, C, D, right? So I've made a list and I've figured out that 9, A, 10, 20 and 46 are the characters which are missing, or bad characters. Basically the VM actually doesn't render these characters. So now comes the final step, wherein we have to create our shell code, and the shell code we are going to use the MSF Venom. So let's quit this again, or we can do this here, right? So let's paste it here, right? So this is an MSF Venom. We are basically trying to figure out the reverse shell code, and we are explicitly telling Kali Linux that these are the 0, 9, 0A, 10, 20 and 46 are the characters which I don't want, right? So this is the reverse shell. Let's wait while the reverse shell comes. I can quit this. Yeah, so we have the final reverse shell code here, shell code here created, which doesn't have any bad characters. Now let's start the GDB validate. Actually, we need not do the GDB validate. We have to directly run this on your machine, right? So let's quit this. This is not required. So we have to finally we need to have our final exploit, right? So this is how the final exploit looks like. So let me just paste it here, which I've already prepared, and let me explain it to you what it does, right? So this is the final exploit. So I'm basically running this file, right, validate file, on my Brainpan machine, and this is the input which I'm going to give, wherein I will start with the shell code which I just saw generated, right? So this is the shell code, and then you have like 46 of knobs, right? And then you have the EX address, the EX address which I generated here, which I've stored here, right? 80484AF. So that is the one, 80484AF. So that's the address here, right? So this finally forms your final exploit, right? So let me just copy this, right? So what do we do here? We come to this particular window where we already have the access to the file, and the file is basically the validate file. So this is what we are interested in. Let's paste this and hope it works, right? Let's run this. Yeah, there you go. We have some kind of a shell. So let's do who am I. Okay, so I just got logged in as some other user here, right? So let's see if we can go inside cd home. Yeah, what is that inside this? We have like Anansi. So you're going to Anansi, sorry, cd Anansi, I believe, Anansi. Okay, so we are inside Anansi. What is that inside Anansi? We have a bin, right? If we do cd bin, we go inside bin, and what is that inside bin? So we have one file, Anansi underscore util, right? So if you do sudo pipe l here, you can see that from here you can, this particular file root here doesn't have password. There's no password, so I can basically convert to a root and I can run anything and you don't have any password. So what I'll do is I'll just copy the shell file, right, from the bin bash. I'll copy inside this particular folder here, right? I'll copy it into this Anansi util file, right? So let me copy that, paste. So I'm basically copying the bin bash to this Anansi util. Now what will I do next is, let me sudo this particular file. So if I sudo this, there you go. What do you see? I'm the root, right? Who am I? I'm the root. I do cd to root, yes, it is possible. Do a ls, I have something called b.text, and you do cat b.text, sorry, my bad, cat b.txt, and there you go, we have successfully got the brain pan, and we have fuzzed this particular VM. So we achieved our objective. Where so if I have to conclude and summarize what we did, we initially started with exploiting it on a Windows machine. What if this particular file was on a Windows machine, right? So we were able to get the shell access on a Windows machine, and then we realized that our actual Brainpan VM is actually a Linux VM. So how would you exploit that, right? So we did the exact same steps which we followed for a Windows machine on the for the Linux machine, and we are able to get the root access as well. Thank you for watching.